Welcome back to HS Chem Team to another round of your video notes. You're going to be writing these directly in your notebook. Pages will be provided by your teacher. And today's topic is the electron cloud model and electron configurations. So let's get started. So the electron cloud model is also known as either the modern model or the modern theory and the wave mechanical model. So this is our most current and up-to-date atomic theory. Where we left off in class would have been Bohr's planetary model. And this is a little bit different in that instead of thinking about our electrons in those perfect orbits, we're still going to have energy levels, but these energy levels are now going to be three-dimensional areas that can contain electrons, or three-dimensional spaces around the nucleus that have electrons in them. And electrons move very quickly. We're close to the speed of light, so they're not easy to see. So you got to think that these electrons are moving around the nucleus so fast in a three-dimensional sphere, if you want to look at it that way, around the nucleus, that it's going to look hazy or cloudy. So the darker the cloud is, the more probable an electron is going to be there. And so this is also in this model where we get this term of an orbital. And an orbital is just the probable location that can hold two electrons. So there are lots of orbitals, an infinite amount of orbitals around the nucleus, and every orbital is an area or region that can hold or have two electrons in it. And it's going to be represented similar to what you see here, where you're going to have a band or an area that is going to have a darker cloudy area to it, and the darker it is, again, that is the higher probability that you're going to find electrons there. Okay, so here's some other ways to look at it. Over here on the left, we have two models of helium. The first one being the planetary model. Remember, we get this from Niels Bohr. This is what we use to draw out atoms in a two-dimensional way, because this is the easiest way to represent our atoms and put our electrons in the correct energy levels. So we still have energy levels in both. It's just that this one, when we're talking about the planetary model, is the easiest for us to actually diagram and represent our atom. But if we look down and compare our planetary model to our electron cloud model, again, you have this area. So we have this area or region, this cloud around where you can actually hold or find electrons. And they're moving so quickly in that cloud that we can't see them, but they're moving all the way in three dimensions around the nucleus. Now, for our purposes, where we're at now, we're going to just leave it as these energy levels are in clouds where we can find electrons, and within those energy levels there are different orbitals. It gets much more complicated than that, but for our introductory purposes, as you can see over here to the right, it does get more complicated. These are some of the shapes of the different energy levels and sub-levels that our electrons can be found in. But we're going to keep it as simple as possible for now and keep our energy levels at, and think of them as the orbits or the rings that we were seeing from the planetary model. Okay, and that brings us into our next topic, which kind of builds off our idea of these energy levels, and that is what an electron configuration is. Now, an electron configuration is a shorter way of showing the location of all of your electrons, and we're going to actually be looking at the electron configuration that demonstrates the electrons in each energy level. So if we had a Bohr model for potassium, it would look like this over here. And so in our potassium nucleus, there are 19 protons, which means there are also going to be 19 electrons outside our nucleus. All right, and with those 19 electrons, we know that they can't all be in one spot because they're all negative, and like charges do not want to be next to each other. So we're going to put them into their specific energy level or principal energy levels. and electrons always want to be as close to the nucleus as possible, but has that energy level. The first one has the least amount of space, so that can only hold 2. And so if we're going to write the electron configuration for potassium, what you're going to do is actually show the number of electrons in each principal energy level, starting with the innermost or the first energy level. So if we were to look at this, the first energy level has 2. The second energy level has 8. The third energy level has 8 as well, to get us to 18. And then our fourth energy level has 1. So instead of drawing this all the way out, many times as chemists we will use the electron configuration to show where the electrons are. And there's a couple reasons for this. Number one, it's easier than drawing it out. And number two, it can tell us which electrons to focus on, which will be coming up next in some of the other videos, is that we're going to focus on the valence electrons. But for today, we're worried about just putting our electron configuration down. So there's the electron configuration for potassium. This is also found on your reference table. So if you go to the periodic table that you have in your reference tables, the electron configuration is always going to be found down here in the lower left corner underneath your atomic number. So that already maps out where the electrons are in terms of their energy levels. Your periodic table is also kind of divided into energy levels. So if we find potassium, which is over here number 19, we should see our 2881 that we just wrote out. And another way that you can look at this is that potassium is in the 4th row. You can kind of treat that like the energy level. So the first row, if we were going across, there are 2 elements. So we have our first energy level having 2 electrons. The second row of the periodic table has 8 elements going across, and we have 8 in our second energy level. The third row also has 8 elements going across, and we have another 8 in our third energy level. And then potassium is the first element in the 4th row, so it only has 1 electron in its last energy level. Okay, so this is, now that you know where to find it, this is pretty straightforward to find the electron configuration for some of these elements. So if you had to draw the Bohr model for an atom of nitrogen 14 and write its electron configuration. So first off, if you had to draw the Bohr model, you need to know protons, neutrons, and electrons. So let's start with that first. And we know that if it's nitrogen, we would find nitrogen on the periodic table. So let's go back to it. And nitrogen is up here, where it is number 7. So that tells us that since its atomic number is 7, nitrogen has 7 protons. And we know that if we write out our isotope with the number behind it like this, that is the same font as the name, that 14 is our mass number. And to get the mass number of an atom, you take protons plus neutrons. So 7 plus 7 gets me to a mass of 14. And the next trick is that this is an atom of nitrogen. And we know that if we are given an atom, that means it's neutral. Anytime we have a neutral atom, the protons and the electrons are also going to be equal to each other to neutralize each other out. So this atom would have 7 protons, 7 neutrons, and 7 electrons. So in the nucleus, you would have 7 protons, 7 neutrons. But the key we're going to look at for the Bohr model would be where are the electrons. So we know we're going to have to put 7 electrons around this nucleus. So our first energy level is going to have 2 electrons. And typically they're going to be drawn on opposite sides to show that they are not near each other inside that energy level. But that first energy level can only hold 2 electrons, so we're going to have to move to the next energy level. We have 5 more to put on there. Okay, so there's our Bohr model for nitrogen. If we wanted to give the electron configuration, this one's a rather simple one. Its electron configuration is a 2, 5. So 2 electrons in the first energy level and 5 in the second. All right, one more before we're done. And this is just to throw a little curveball at you. Draw the Bohr model for a fluorine 19 -1 ion and give the electron configuration. All right, so fluorine 19, we're going to do the same thing we did last time. Let's find the protons, neutrons, and electrons. So go back to your periodic table. And let's find fluorine. And fluorine is just a couple away from where nitrogen was, and it is number 9. So we're going to use that for our protons. So we know that fluorine has 9 protons. Again, the number that is big is the same size font as our name. That is going to be our mass number. So fluorine 19 has a mass number of 19. So to get our mass, it's 9 protons plus 10 neutrons in this case. And our electrons, now this one is going to be a little bit trickier because now we have a -1 charge. And we know that we can find our charge by subtracting your electrons from your protons. So right away we know that our charge is a -1. Your charge, if there is one, will always be superscript, so raised to the upper right, equals 9 minus our number of electrons. So that means our electrons in this case is going to be equal to 10. We're going to have 10 electrons. Alright, so let's draw this out. We know in our nucleus we have 9 protons and 10 neutrons. Outside of that, we have to place 10 electrons. So that first energy level, like always, can only hold 2. Then we're moving to the second energy level, and we have to get to 10. So we have 8 left over. We're going to fill this in with 8 electrons. Which means the electron configuration for our ion of fluorine, so in this case we're dealing with an ion, which makes things a little bit trickier, we can't take it directly from the table, is going to be 2, 8. That does it for the electron cloud and electron configurations. So this is just our start to this. Bring questions to class tomorrow. Good luck.